Today's background is also technology. You'll remember from the last lecture, the background was the radio telescopes at Narrabri, and I think pretty much anyone will spot the technology there. You've got these giant dishes pointing at the sky, trying to understand the depths of space. The background I have here is the Brewarrina fish traps on the Barwon River in western New South Wales. I guess the reason why I like to put this photograph right after the radio telescopes is that it basically points to technology being a constant. So what you're seeing here is a whole pile of rock formations, human-made, that are basically designed to enable fish to still move up and down the river, but some number of them sort of get trapped, and that makes it quite easy to go in there and catch them. And essentially what you've got is a local sustainable fishery built such that you harvest some number of fish without an enormous amount of work and let the rest keep going so that you don't eventually starve. And when I say technology is a constant, what I basically mean is that us as humans have pretty much for our entire history been doing this process of learn about our world, use that knowledge to improve our life circumstances or generate new knowledge in either way, and then go through that iterative process again and again and again. And it's not necessarily now that we have this thing. We've always had this thing. We've just been solving different problems as we've gone along. Okay. All right. So thinking about knowledge in the context of where we are in the course, I guess if I think about the entire 12 lectures I give across 4 weeks here, I could point out two conceptually difficult points in the course. If you're a bit of a rock climber, you'll know what a crux is. It's kind of the bit where you get up the wall and all of a sudden it gets really hard. And then once you get past that point, it's actually pretty easy again. The course, my half of the course kind of has two cruxes. One of them was the first half of the lecture we just did, and the other one comes at the end of week 3. And the one we just did is difficult because what we've done is we came through looking at our spin systems, and everything's kind of simple because we're doing 2 by 2 and we know what up and down is and so forth. And then once we got into lecture 4, we sort of made this subtle shift towards being a bit more general about things. We started looking at n by n matrices instead of 2 by 2 matrices. We started to look at eigenvalues without calling them up and down, or eigenvectors and calling them up and down, or eigenvalues and calling them +1 and -1. And this approach to generalization is really common in physics. You get used to it after a while. But what I want to do in this half of the lecture and in the next lecture is sort of start to filter those general ideas we had from lectures 4 and the start of lecture 5 back into our 2 by 2 spin system to give you a bit of a picture how this fits together. Okay, so let's look at how to build our spin operator Z. And there's a couple of pieces of information that we have in order to build this together. The first is that each component of our operator, and we'll call it sigma to just represent the spin, so Greek letter for S. Each component will be represented by a Hermitian linear operator. So if we're measuring along Z, we'll have a sigma that's called Z. If we're measuring along X, we'll have a sigma that's called X. If we're measuring along Y, we'll have a sigma that's called Y. And later on, we'll have a sigma that points in any direction we like. Okay, so there will be an operator for every single possible measurement that we could ask, which is every single orientation we could put our Stern-Gerlach experiment into. The second thing that we know is that the eigenvectors of a measurement along the z-axis will be up and down. And we know that the corresponding eigenvalues are +1 and -1, okay? And so what we can do is we can write a pair of eigenvalue equations that look exactly like this, okay? And the third piece of information that we have, but we don't necessarily need to use to get this, is that the states up and down are orthogonal, which basically means the inner product of up and down will be 0, okay? So let's bring up a page. And what I'll do is basically work through quite simply how to build sigma Z from stuff that we already know, okay? It's actually pretty easy. So we have our two eigenvalue equations, right? So sigma Z acting on up will give us up, and sigma Z operating on down will give us minus down. And just to make this really clear for a second, what I'm actually doing here is plus 1 up and minus 1 down. Okay, so these really are eigenvalue equations. What we're saying is that the operator connected to measurement along z, which is sigma z, will act on the eigenvector u. It will give us the corresponding eigenvalue, which is plus 1, times the original vector, which is u, and similar idea for down, okay? And of course, there you'll get a minus 1, all right? And of course, we usually don't show the plus 1 or the 1 in the minus 1. We just write them like they are up here. But just so you're really clear that that's what's going on, I've written that down on the page there. Okay, what we can do here is basically assume that, let's call this 1 and let's call this 2. We can basically assume that these two things are matrix and vector equations. So what we can do is take 1 and we can write it a little bit like this. Sigma z 1, 1, sigma z 1, 2, sigma z 2, 1, sigma z 2, 2 times our up vector will be equal to our up vector, okay? And we can also write something equivalent for our down, which will be sigma z 1, 1, sigma z 1, 2, sigma z 2, 1, sigma z 2, 2 times 0, 1 will be equal to minus 0, 1. Okay, let me just get this to be a proper bracket. I get a bit scribbly when I get to the edge of the iPad. Okay, all right, so what we can do with these two equations now is just to try and solve what the elements in the matrix are. And I guess it's probably not formally the right way to do it, but in my own head, sort of the fundamental idea of linear algebra is that matrices, what you're really doing is coming up with a smarter way to write simultaneous equations, okay? So if we look at 1, what we know is that if we do our multiplication in here, let me do this one explicitly. Sigma z 1, 1 times 1 plus sigma z 1, 2 times 0 will be equal to the element at the top, which is 1, okay? And if we do this, basically what we'll arrive at is sigma z 1, 1 is equal to 1, right? So all I've done is taken the top row of the matrix, multiplied it by the vector beside it to get the element at the top, and used that knowledge to tell me what the answers are there. We also know in there that sigma z 1, 2 could equal anything. And it could equal anything because when we do that equation, we basically go through and the 0 knocks it out. So we don't know anything about it. I could also write here question mark. I don't know anything about that element yet. If I now think about the other multiplication, so I take the bottom row and multiply it by the vector and get the bottom element, right? What I would be getting is sigma z2 1 times 1 plus sigma z2 2 times 0 is equal to 0, okay? And if I work that through, what I know must be true is that sigma z2 1 must be equal to 0, and sigma z2 2 can also be anything I like, okay? Just working through the exact same logic for bottom row to column to bottom element. I can also apply this same logic not just to this first equation at the top, but to this second equation here, right? And so now if I go top row times the vector, I've got sigma z1 1 times 0 plus sigma z1 2 times 1 will be equal to 0. And that means that what I can do in here is go sigma z1 1, I don't know anything about it. Sigma z1 2, I know it has to be equal to 0. And then likewise, if I do the bottom, I've got sigma z2 1 times 0 plus sigma z2 2 times 1 has to be equal to 1. That means that I know that sigma z2 2 has to be equal to 1, and sigma z to 1 can be anything I like, okay? Now, what do I know? I know that these two equations that I have over here can hold simultaneously. So each of those, because it's a 2 by 2 matrix, is basically two simultaneous equations and two simultaneous equations. But I know that those two matrix equations hold simultaneously as well. So what I've really got is 4 simultaneous equations split into 2 sets that all hold together, right? And so if I look at this now, what I can do is go, I know that from this top part that sigma z11 is 1, or from this bottom part could be anything, and 1 can be anything. It's perfectly okay. So what I can do is I can make it 1. Then similar, I can look at this sigma z21 here, and of course it's 0, and it's consistent with it being anything in the second equation, so let's call it 0. Then if I look at sigma z12, my second equation tells me it's 0. The top one says it could be anything, so 0 is probably okay, consistent with both. And then this element here, sigma z22, would be 1. Actually, I've made a mistake in here, which is this has to be minus 1. Let me explain why this has to be minus 1. This has to be minus 1 because when I did the multiplication up the top here, I forgot about this minus sign at the front, right? So what I'm really doing in this second equation is going sigma z21 times 0 plus sigma z22 times 1 is equal to minus 1, right? So this element down here is minus 1, and that will give me a minus 1 in there, okay? This thing is basically just sigma z, okay? Fairly simple line of logic. The one set of elements that I can choose in there that behave themselves in terms of that equation is perfectly fine. So let's just check this for a second and make sure it works. If I take 1, 0, 0, minus 1, and I multiply it by 1, 0, what I would get is 1 times 1 plus 0 times 0 is 1. And I'd get 0 minus 1 times 1, 0. So it'd be 0 times 1 plus minus 1 times 0 is 0. So that behaves itself properly. And I would have 1, 0, 0 minus 1 times 0, 1 here. And if I do that, I will get 1 times 0 plus 0 times 1 is 0 at the top. And I would have bottom row 0 times 0 plus minus 1 times 1 is minus 1. So that'd be minus 1 in here. And of course, I can divide that by minus 1. So this would be minus 1 times 0, 1, which is just minus 0 and 1. So we know that this works, okay? 2 points here. One, when you're doing questions, keep an eye out for making little errors like that. I could have walked straight on past that if I was sloppy, but I'm always, while I'm doing these lectures, trying to think back, where am I making a mistake, and then just catch them. And the other is that when you get to an answer, sometimes it's actually, if you've got enough time and you know you can do it quickly, it's actually good just to check that your answer is consistent with what you would expect, which was this bit that we did at the bottom, okay? All right, so what we get here is basically just a matrix that looks like this. Sigma z is 1, minus 1, 0, 0. And you can see it's entirely consistent with what we were talking about in the earlier parts of the lecture, right? For our spin up, spin down system, there's two eigenvalues, plus 1 and minus 1. Those are on the diagonal, right? The off-diagonal elements are zeros, so we've got a diagonalized 2 by 2 matrix, and our eigenvectors would be 1, 0, and 0, 1. So this whole diagonalizability argument holds. And of course, this whole idea that, you know, our eigenvalues correspond to eigenvectors, which are then our basis states, that works as well, okay? Pops out kind of nice and simple and helps you make sense, hopefully, a little bit of what we were doing with operators earlier in a more general n by n sense. Okay, and you'll notice that these are well behaved in terms of the matrix being Hermitian as well. So the diagonal elements are real because they have to be their own complex conjugate, and the off-diagonal elements are conjugates of each other, and of course 0 is its own conjugate without any problems there. And you'll notice I never needed to use this orthogonality relation, except that I know that the two vectors up and down already are orthogonal. We proved that in an earlier lecture. Okay, so with sigma z done, we should be able to use the same tricks to get sigma x and sigma y, okay? And we can do that I'm going to do sigma x, and then I'm going to let you do sigma y for yourself for no other reason than that it's good practice in how to do this, and you'll have the answer in my notes, so you can basically consider it a sort of a homework exercise. So how we start with sigma x is we know from an earlier lecture that we had a way to write our states R and L, right? Because if we're measuring along X, our basis states or our measurable outcomes are all either spin points to the right or spin points to the left, right? We can write these as 1 over root 2 up plus 1 over root 2 down, and 1 on root 2 up minus 1 on root 2 down. Okay. And if we want to write these as vectors, they're pretty easily written as 1 on root 2, 1 on root 2, and 1 on root 2 minus 1 on root 2. Okay, and our eigenvector equations or eigenvalue equations will look like this. Sigma x acting on R will give us plus, sorry, that should be an equal sign, equals plus 1 R, and sigma x left will give us minus 1 left, okay? All right. So what we can do here is basically work this up in matrix form, same as we did above, right? So this would be sigma x 1, 1, sigma x 1, 2, sigma x 2, 1, sigma x 2, 2 would be multiplied by 1 over root 2, 1 over root 2 is equal to 1 on root 2, 1 on root 2. And sigma x 1, 1, sigma x 2, 1, sigma x 1, 2, sigma x 2, 2, 1 on root 2 minus 1 on root 2 will be equal to minus 1 on root 2 minus 1 on root 2 down the bottom here. All right. Can call this equation 1, can call this equation 2. And of course, as you know, both of those correspond to two simultaneous equations. Those two eigenvalue equations both hold simultaneously. So what we're actually solving is 4 simultaneous equations that we can automatically split into 2 pairs. Okay, so the next step here is I'm going to try and pull out the equations, and you notice that I'm going to drive you and myself crazy with all these root 2's. So what I'm going to do is just factor out all the root 2's here, just to keep things nice and simple. So what I'm going to do here is go sigma 1, 1 plus sigma 1, 2 is equal to 1, right? So let's think about this. What I'm doing is I'm taking the top row of the top equation here, so this bit here, and multiplying it by this bit here to get this bit here, and then dividing the two sides by some factor to get rid of the 1 over root 2's, okay? And so what I'll get is sigma 1, 1 times 1 over root 2 plus sigma 1, 2 times 1 over root 2 will be equal to 1 over root 2. Pull the 1 over root 2 out the front, divide the two 1 over root 2's out. Sigma 1, 1 plus sigma 1, 2 is equal to 1, okay? Do the same logic on the second one. So basically take the second row here, multiply it by this guy, and transfer it across to that guy. And so I would get sigma 2, 1 plus sigma 2, 2 is equal to 1. And then for the second equation, I can do the same thing. So I can take the top row times the thing to get to the end. So it would be sigma x1, 1 times 1 over root 2 plus sigma x1, 2 times 1 over root 2 will be equal to minus 1 over root 2, right? So this would, once we cancel out the 1 over root 2's, be sigma 1, 1 minus sigma 1, 2 equals minus 1. And the corresponding equation for the bottom row, when we take it across, will be sigma 2, 1 minus sigma 2, 2 is equal to plus 1, okay? I'll let you go through and work those for yourself more slowly. I've basically got half an hour to get through this, and the idea is not that you just do the half hour and you magically know it. Often for some of the things you have to do in lectures, you actually want to come back later and do it for yourself, slow down a little bit, and make sure that you get all the steps in between. In much the same way that when I write this course, I have a textbook that will jump, 15 or 20 lines of algebra. Will go, we get this, and then we do blah, blah, and then we get this. And my job is actually to sit down and do every step in that equation as well, so I can write things like my notes that actually break down the steps in the notation for you, okay? All right. So what we know is we can couple these into pairs, and we can handle those pairs one by one, okay? So what I'm going to do is I'm going to handle the first pair. I'll call it pair A and pair B. I'm going to handle pair A. And what I'm going to do is show you basically my little mathematical trick for doing simultaneous equations side by side fairly quickly. You may have your own tricks, and the point of this is not that you learn my tricks. The point of this is that you should make sure that you have a box of tricks that are just mathematical things that you know how to do. Many of you won't have had me before because I don't teach first year anymore, but when I was an undergraduate, I used to keep a book, and I used to call it like the book of maths, and I would have all my mathematical tricks in it. So whenever I was in a course and I learned some trick for doing something, I'd add it to that list. In the first few years, it was how to do little things like this, solve simultaneous equations quickly. In later years, it was approximations to use to solve equations and stuff like that. And right at the start of the exam period, I'd square off a couple of hours to actually pull out that book and have a look and just freshen in my mind all the tricks that I had for maths. And it was less a memorization of them and more a just, I can do this, I can do this, I can do this, I can do this. It was sort of just knowing what the possibilities are for solving mathematical problems. Okay, so if you don't do that already, highly encourage it. Okay, so let's break these into pairs. We've got sigma 1, 1 plus sigma 1, 2 is equal to 1. And let me just fix this 1 here just so that no one thinks it's a 2. And I've got sigma 1, 1 minus sigma 1, 2 equals minus 1. And so what I'm going to do here is actually correct myself. What I'm going to do to break up these pairs is, because all these equations hold at once, what I'm going to do is make one pair here, which I'll call A, and one pair in here, which I will call B, because that's the easier way to solve them, actually, is to split them off into the way they hook up with each other. Okay, so what I can do, and the reason why I do simultaneous equations like this, writing them as two columns, is that I work down one, then jump to the other, work down the other, and then jump between them, okay? So my first step here is that I'm going to write this equation on the left in terms of sigma 1, 1. So sigma 1, 1 will be equal to 1 minus sigma 1, 2. And then what I can do is use that up into here, okay? So if I do that, I've now got 1 minus sigma 1, 2 minus sigma 1, 2 is equal to minus 1. I can expand that out. So 1 minus 2 sigma 1, 2 is equal to minus 1. I can subtract the 1 across. So what I'll get is minus 2 sigma 1, 2 is equal to minus 2. And then sigma 1, 2 is equal to minus 1. And then I can take that result back and put it back in here to get my other half. So this will now be sigma 1, 1 is equal to 1 minus sigma 1, 2, which is minus 1. I have a problem here for a second, which is that this should be plus 1 because I divide by 2 there, which means that's plus 1, and this is 1 minus 1, which is 0. That's better. Okay. So again, one thing sometimes to do is to spot where you're making mistakes, or you'll notice what I did then was go, hang on, something's not right. Something doesn't feel right here. I've made a mistake somewhere. Go back and hunt it down. This is one of these things when you do enough problems in physics, and this is why I encourage you to do lots and lots and lots of problems. You get used to when that weird feeling, it's like the heebie-jeebies when you're walking out in the bush at night and you think that, something is watching you. I get the same thing when I do maths like this. I get to this point, I go, hang on, something's not right here. I've made a mistake. I must have. And I go back and find it like I just did. Okay. All right. So that's got that one solved. And then we can do the other two in part B up here. Okay. So let's do this. Sigma 2, 1 plus sigma 2, 2 equals 1. And sigma 2, 1 minus sigma 2, 2 equals 1 as well. Okay, so we got this equation and that equation. Same approach. So what I can do here is go sigma 2, 1 is equal to 1 minus sigma 2, 2. I can use that up here. So this is going to be 1 minus sigma 2, 2 minus sigma 2, 2 equals 1. And you'll notice I just dropped the x just to keep things nice and simple. I can put the x back later. Simplify notation. Very handy tip in exams. Just state what you're doing and simplify your notation. Keep it as simple as you can. Minus 2 sigma 2, 2. This would be 1 here and 1 over there. I can subtract the 1 from the left-hand side over to the right. So this is now 2 sigma 2, 2 is equal to 0. And then sigma 2, 2 here will, of course, be equal to 0. I can then feed that back up into here. So sigma 2, 1 is equal to 1 minus 0. And, of course, 1 minus 0 is 1. Okay? Pretty simple. So let's just distill the results. Sigma 1, 1 is equal to 0. Sigma 1, 2 is equal to plus 1. Sigma 2, 1 is equal to 1. And sigma 2, 2 is equal to 0. And if we now just go back up to our original matrix up here, 1, 2, 1, 1, 1, 2, 2, 1, 2, 2, and plonk our elements in, this will now be 0, 1, 1, 0 in here like that. And this will be sigma x. Okay. All right. Big points in this. Make sure your ability to do maths quickly is good. You know, little things like solving simultaneous equations and reducing things. If you don't practice that and you don't make mistakes and learn from your mistakes, you'll never get good at it. There's a lot of people I know who come in and go, oh, I'm just not very good at maths. And you say to them, well, how much time do you spend practicing your maths? Well, I don't. I'm not very good at it. Well, that's why you're not very good at it. You have to practice it like mad. So I sort of trained in maths a bit like I train in sports as a physicist. I spend a bit of time, particularly when I was an undergraduate, less so now, which is why my maths get sloppy sometimes. I used to spend time just practicing my maths. Just to make sure that part of my game was strong as an undergraduate student. And if you're a physicist, you should definitely do that as well. Okay. All right. And so I'll let you do y for yourself. It's a fairly simple extension on what we just did for getting x. And what you'll find is that you get something that looks very similar to it, except there's an I and a minus I that pops into here when you do it. So let's have a look at these three vectors now all in a row and make some observations about what they look like. First thing you'll notice is that the diagonal elements are all real, as you'd expect for Hermitian matrices. 0, 0, 0, 0, 1, minus 1, they're all real numbers. Number two is that the real off-diagonal elements will match in sigma x, right? So you'll notice that this one is equal to this one, and it is because they have to be equal to each other's complex conjugate, right? The complex conjugate of 1 is 1, so those two have to be the same. You'll notice that the off-diagonal elements in y are of opposite sign, and that's because they also have to be conjugates, but because it's an imaginary, you have to change the sign, right? So I is equal to minus I, or I and minus I here, they're each other's conjugate. They're not equal to each other, of course. And then probably fourth one is the most notable and interesting one in here. You'll notice that the diagonal elements here for sigma x and sigma y are 0. And what that's saying is that essentially for the basis that we're using at the moment, and this is an important point on bases. For the basis we're using at the moment, we're dealing with up and down. Because we're dealing with up and down, the corresponding matrix operator for that measurement is sigma z. It will be the one where we care about the eigenvalues and the eigenvectors because it's corresponding to the measurement that we're actually making, right? And when we're in that basis, the other spin states that we get in here will not be diagonalizable. They won't have eigenvalues on the diagonal, and they won't have 0 off-diagonal elements because they're not actually the matrices that correspond to the basis that we're working in at the moment, okay? So you'll notice that these basically have zeros on the diagonal, which tells us that, well, you're not measuring sigma x and you're not measuring sigma y because you're in the up-down basis. I don't have time in this lecture to do it, but for those of you who are interested, you can do it as an exercise, and I'll put this up in my exercise section in the course notes. Those of you who are sort of following to this point will probably go, well, hang on a second, what if I work in my left-right basis and I'm doing sigma x? Then shouldn't sigma x be the one that's got the eigenvalues on the diagonals, and then sigma z and sigma y are the ones that look different? And the answer is exactly yes. Okay, so if you go and do a change of basis here to measuring along x, so that right and left are your basis states, then your sigma x matrix will look like your sigma z matrix, and your other two, sigma z and sigma y, will look like your sigma x and sigma y here. And all you're really doing is just changing the basis. Okay, so in this sort of spin thing, which basis it is you choose will determine which one of these three operators will look like the form that has the eigenvalues for the measurable outcomes on the diagonal, and the other two will have the corresponding form themselves. Okay, there's two ways to do that problem. One is to just go back and work through all the algebra we did for the different bases. The other is that you can, if you know that change of basis corresponds to rotation, you can enact a rotation operator on that and find the answer. Okay. If people want to try the second option using rotation matrices, if you're a really keen student, you want to practice your skills, have a crack. I'm happy to have a look at it if you manage to do it or get stuck. It's always cool to have a little bit of extension problems in the course. The thing you have to be really careful about is that people then start to make the assumption, well, you know, if I operate sigma z on my state, then I'm doing a measurement of sigma z. The answer to that is not quite. Okay, so the job of spin operators, sigma z, sigma x, sigma y, or any operator that's connected to an observable for that matter, is to tell you what the measurement outcomes can be. That's all its job is in the end. And so formally, the spin operators take a form so that the eigenvectors will be the possible state vectors resulting from the measurement. In other words, you know, what you'll get is up and down, and the corresponding eigenvalues you will get is +1 and -1, which corresponds to physically what the angular momentum is. Okay, and you'll remember that we basically turned h bar into 2 at the start so that we can make that be 1. So for example, for sigma z, it exists for no other reason than to tell you that the possible eigenstates are up and down, and the two possible measured values for the z component of the spin are +1 and -1. Okay. The point that I really want to reinforce here, because it's a very common error when people come to this point in the course, which is to think that operators, the spin operators, sigma x, sigma z, sigma y, will give you probabilities. They don't, right? You remember back to lecture 3, the probabilities come from the projection operators. So the outer products up, and down, okay? That said, the operators do tell you what are those basis vectors you need to use in the projection operators, okay? And so what I'm really trying to do here is dispel, right at the end of this lecture, a really common misconception, which is that measuring an observable is the same as operating with the corresponding operator on the state, okay? And to very quickly give you an example of why this doesn't work very well is to ask the question, what if we apply sigma z to r, right? If we came into this with the sort of mistaken idea that applying sigma z to something is the equivalent of measuring the outcome of measuring sigma z for a spin point to the right, we know from earlier on that there's two possible outcomes. There's an up and a down, right? If what you do is make the mistake and go, well, you know, what I should do here is basically just apply it. Let's imagine sigma z on r, okay? What we would have here is sigma z being applied to 1 over root 2 up plus 1 over root 2 down. And we could write this as 1 on root 2. Let's take the 1 on root 2 out the front. It would be our matrix operator, 1, 0, 0, minus 1, times 1, 0 here, plus 1, 0, 0, minus 1 times 0, 1, like that, okay? If I do this, I can do the multiplication. So I've still got my 1 over root 2 out here. I would have 1 times 1 plus 0 times 0 is 1. And then 0 times 1 plus minus 1 times 0 is 0. So that's the multiplication on the first set. And then let's do the multiplication on the second one. It's 1, 0 times 0, 1. So that would be 0. And 0 times 0 plus minus 1 times 1 would be minus 1 just here, okay? And of course, this thing would be 1 over root 2. This vector here is just up. This vector here on the right is just minus down, because down is 0, 1, so we can take the minus 1 up the front. And of course, this thing is just left, right? And so what you'll realize here is that applying sigma z to r just gives you left. It's not doing the measurement for you. All it's doing is exactly what an operator should do, which is act on a state vector to give you a new state vector. And in this particular case, all that sigma z does when it operates on r is give you left. It's not very useful, not very meaningful. It's not going to get you a probability. It's just, I used in the wrong way. If you use sigma z on up, in contrast, sigma z on up will give you up, and that's telling you that up is an eigenvalue of sigma z, an eigenvector of sigma z, and the corresponding eigenvector is +1. And so what it's telling you is that one of the measurement outcomes for sigma z is up, and the corresponding eigenvalue is +1. Okay, so what I want to make a really important point of here is be very, very careful. The spin operators don't exist to get you probabilities. You get probabilities the way we did it in lecture 3 using projection operators or inner products. Spin operators exist primarily to tell you what the eigenvalues and eigenvectors are. And as we'll see in the next lecture, you can build them together in order to extend the problem out into measuring the spin along any particular direction you're interested in. Okay, so I think I'll finish there and see you in the next lecture.